your collaboration with the Institute and learning more about what you're doing, and to have opportunities for more exchange between the physical oceanography departments. Yeah. So I am at JPL. My job title is climate scientist, but I primarily work as an oceanographer, physical oceanographer. And one of the projects that we work on, that I'm here to talk to you about today, is a project called ECCO, which stands for Estimating the Circulation and Climate of the Ocean. And this project began 25 years ago, which is unusual for NASA, because most NASA missions or projects last as long as the satellite lasts, or as long as the spacecraft lasts. So 25 years is a very unusual, but it says something about the commitment of NASA to understand the ocean and to understand climate change, that we keep going. So this project today is a collaboration of many people at several different institutions. Maybe one day Successi. Okay, so the project, the general idea of the project is to create reconstructions of how the global ocean has changed. So originally, the idea was to combine measurements from ships, physical oceanography measurements from ships, and also measurements from satellites, mainly sea surface height. And the idea was these are two very different kinds of measurements, and it can be difficult to put them together in a single framework to understand how the ocean is changing. So that's kind of like the big picture idea, and it began with just physical oceanography in the tropics and mid-latitudes, and over the years it has expanded to include polar oceanography. It has expanded to include biogeochemistry, and now also some more work with air-sea interaction. Within the ECCO family, we kind of separate into we have two cousins. One is what we call the state estimate. So this term, state estimate, is similar to the term of atmospheric reanalysis, in that we want to make a single story about how the ocean has changed. We want that story to fit all of the observations, as many data as we can, from ships, from Argo, from all the satellites. We want the best possible reconstruction of how the ocean has changed. And that's a hard problem, and we'll talk a little bit more about that. But generally, what we can do today is to make a simulation of the planet Earth at about 1 degree or 1/3 degree spatial resolution for 30 years. Okay, that's one kind of application. Another application we call the high-resolution simulations. So these are simulations that use NASA's biggest supercomputers, and we try to resolve all kinds of physical processes on the small scales. So for example, in the 1 degree state estimate, we don't have internal waves. We don't have a good representation of many physical processes. But in the high-resolution simulations, we can resolve some of these processes, the processes that some of your students here today are working on, and some students, and like for example, what Hector worked on. So those are very important, in particular because they also help us formulate new missions. And at the end of my talk, I have a few slides from your former student here, Hector Torres, to show how he's using ECCO today to help formulate a new satellite mission for NASA, which I think is super cool. Okay, so let's step back a little bit, because not everyone here is an oceanographer, not everyone here is a physical oceanographer. And I want to just spend a few minutes to describe why understanding the ocean is fundamental for understanding climate change. Climate change and the climate of Earth today. Okay? So, overall, the planet Earth, the climate of planet Earth could only be like it is because we have this ocean. The ocean stores a tremendous amount of heat, Of course, it's fundamental for the water cycle. And today, with global warming, it also absorbs a lot of carbon dioxide. So for these reasons, the ocean is fundamental, and so we need to understand how the ocean works and how the ocean is changing. One good example of why the ocean, I would say, is more important than the atmosphere, even though, of course, we breathe in the atmosphere, we need the atmosphere, is the ocean can store 1,000 times more heat per unit mass than the atmosphere. Excuse me. 4 times per unit mass, but 1,000 times more in general because the oceans are so big. A common exercise I have students do is to ask, how warm would the air be today if we didn't have the ocean and we only had the global warming carbon dioxide? And the answer is we would already be dead. The Earth would already be toast. It would already be too hot to live. So if it wasn't for the ocean, global warming would have already finished civilization. So that's important. We probably all know that the energy from the sun, it doesn't come to every place on the Earth at the same amount. There's more energy comes in at the tropics. This figure on the right shows the combination, left and the right shows where the energy comes in. But where does the energy come out from the ocean to the atmosphere? It doesn't come out at the same place it comes in. More energy comes in at the tropics and it goes out at high latitudes. That's how Western Europe is able to be a habitable place and not a frozen wasteland. So this map on the right shows at every place on the Earth where energy is coming in, on net in, that's red, or net out, that's blue. And because they are separated, we obviously need to know how the ocean moves the heat from the tropics to the higher latitudes. And how, with global warming, those movements of heat change. Yeah. Of course, we know the ocean is a tremendous reservoir of water. There's 100,000 times more water in the ocean than in the atmosphere at any one time. 100,000 times more, which is amazing. We also know, because of the hydrological cycle, that where water comes into the ocean isn't the same place as where it comes out of the ocean. So a map on the right it shows how much rain there is over the oceans. The more red means the more rain. And you see here in Ensenada, it's like zero rain. The same thing with Los Angeles. Except for this year, with 12 Rios atmosphericos, it was too much rain. But this is where the water comes in. But this is the net. So this shows red where the water comes in more on average than it comes out, and blue where it evaporates more on average. And again, they are very different. And for the planet to be, the cycles to be in balance, the fresh water has to go from here and leave there, and ocean circulation is needed to know how it happens. It's a very interesting map. It's very interesting. And finally, with carbon. The ocean stores 50 times more carbon than the atmosphere. 50 times. And where the carbon comes in, where the ocean absorbs carbon dioxide, is different than where it releases carbon dioxide. So it's the same kind of map and the same idea. We need to know how much carbon is the ocean absorbing and how is it moving. Some of it is going deep in the ocean, keeping us safe on the surface. How is that circulation changing? It's an easy question to ask, but a very difficult question to answer, and really a lot of work is put on this subject. Where is the carbon going? How are those processes changing as the climate warms? Okay. So just with that little background, which most of you in this department of oceanography already know very well, we established the ocean is a key element of the climate system, and that the places where the heat, fresh water, and carbon go in are very different than the places where it goes out. We need to know about ocean circulation and the variability of that circulation to understand those patterns. And we need to know how they're changing through time. So in order to understand climate change and climate variability. That's why I like this project, because the scope of the mission of the project is multiple decades. And, the ocean changes slowly, but it does change. And we need decades to see those changes. Some of them are very slow, and it's also very hard to measure the ocean. I learned about the ship that Successi has, and you guys all know about the different projects to go and measure the ocean. The ocean is vast, and we are very small. And going to sea is very expensive. Sometimes we can only see a little tiny part, right? But we need to know how the whole is changing. And that's what the ECCO project, that's what the mission is. To understand the whole change, even though we only observe little parts. Okay. So now I'll talk a little bit about the observations, how we observe the ocean. So we have here like the traditional oceanography, which you are probably mostly familiar about. Traditional oceanography involves going to sea. And I'm curious, how many people in this room have ever gone to sea for their science, for work? Yeah, most of you. I've gone to sea a couple times. Yeah, like half of you have gone to sea. So you know how difficult it is, how difficult this kind of work is. Before the 90s, the measurements in the ocean were kind of random, and they were often just 1 year, okay, maybe one country will go here, another country will go there, and then they wouldn't go back for 20 years or maybe ever go back. So it's hard to understand how the ocean is changing when you never go back. So there was a campaign, the World Ocean Circulation Experiment, now Ghost Ship, this map on the top right, where ships would go regularly every year or every few years to measure these long lines, cross sections of the ocean to see what was happening there. But even with that very intense international campaign, we still don't know a lot. But that's traditional oceanography. In the mid-2000s, there was a revolution in physical oceanography with the invention of the autonomous profiling floats. The major program today was called Argo. And these are incredible instruments that they're robots. They last between 3 and 6 years. They float at 1,000 meters. They fall asleep for 10 days. And every 10 days they wake up. They turn on their instruments. They dive to 2,000 meters. Then they go all the way to the surface. They measure the whole way. And when they get to the surface, they send the data over satellite. At any given time, there are about 3,000 to 4,000 of these floats moving through the oceans, just floating randomly. And every year, countries put new ones in as the old ones die. And there are more measurements from Argo, more than 2 million measurements now, than there have ever been in the history of mankind from a ship. Because these things they never sleep. They don't get seasick, and they can go everywhere. It doesn't matter, and they are amazing tools. Most of the time they're deployed from a ship, but every once in a while you can also throw them out of an airplane, which is more fun. Definitely more fun. So those are the in-situ measurements, and then from space, of course, NASA and other space agencies measure the ocean from space. The principal measurement for physical oceanography is the altimeter, which measures the elevation changes of the ocean. We've been doing this for 33 years. If you want to be really safe, you can say 45 years, because 45 years ago there was one experimental mission called CSAT, which for 107 days measured the ocean surface. as an experiment. But the real high quality measurements of sea surface height have come from 1992. We have unbroken record of sea surface height around the whole planet from these series of satellites and also others. But this is a super important measurement. We have sea surface temperature, which is Professor Vasquez's favorite parameter. This measuring the temperature of the surface, we all know is very important, because if you live close to the coast, the ocean sea surface temperature determines your climate. It determines the rate of exchange between the atmosphere and the ocean, and is also an important indicator of global warming. So we have sea surface temperature measurements. We have, recently we have sea surface salinity measurements, which is a technologically amazing accomplishment. When I was a graduate student, my advisor told me, we could never measure this. This could not be measured. And that's how far, and that wasn't that long ago. And that's how fast the technology can change. That now, not only can we measure it, but it's regularly measured. And even new data sets for this are coming out, even last week, new data sets. And the sea surface salinity is fundamental because it tells us about the water cycle. That's a primary thing. Lastly, the last important remote sensing technology is the gravimeter. Can I ask another poll? How many people here have heard of the GRACE or GRACE follow-on missions? We've got almost 3 people, including myself, 3 people. Professor Gomez has heard of it. He's just not raising his hand. 4 people. So these satellites are super interesting technology. It's a pair. A pair of satellites. They fly like in a caravan. And they send a laser pulse back and forth. And they count how much time it takes for the laser to go back and forth. And when the first satellite encounters more mass, it could be from a place where there's more seawater or more mountain, it speeds up because of the Newton's law of gravitation. So the time between the 2 satellites increases. And then this one comes and it speeds up. And this one goes and it goes further away. And all day long, they just go like this, like a spring. They collect all of those measurements, and they finally, at the end, can make a map. How do I go back? Of how the mass on the planet changes. And we say what changes the most is the water. Ocean water, it moves from North Pacific to the South Pacific. It moves from the South Atlantic to the North Atlantic. It moves east and west across the basin. And with this satellite, we can measure literally how the water mass moves around the planet. So, okay. So now I've told you, we have all of these measurements from the ships, from Argo, from the satellites. No one can understand this. That's my experience. It is no human being can understand it. We can make the measurements. NASA has great engineers. Right? They can measure everything. But if you give all of that data to a graduate student and you say, tell me how the ocean is changing, well, where do you even start? It is too much. It is too much information. And of course, people put parts of it together, right? You can combine altimetry and sea surface height and a few in-situ measurements for your PhD. You can study this one little part. That's what, the best human mind can do that. But all of the data, all at once, from 50 missions, 2 million Argo profiles, it's too much. At least I have never met anyone who can do it. So this was what motivated this ECCO project. And I've already made these points. We have too many different kinds of data, and it's too much for one human to understand. So for the ECCO project, what we try to do is first we have the ocean simulation, the ocean model, okay? And what is the ocean model? It is just the place where we put our physical understanding of the ocean, the physics, the thermodynamics, the chemistry. It's the model that has the laws, the conservation laws. That's all it does. It's just the equations of motion, of thermodynamics, of chemistry. We set up the equations in a domain that looks like planet Earth. And we give it seawater and we say it has an atmosphere. But we don't know anything else. Then we tell the model to run. And it tries to solve the equations like we solve the equations. It solves the equations. We give it an atmosphere that blows wind and a sun, a simulated sun that comes up and down, and it looks like Earth. It looks something like Earth. But if you were to say, is it Earth today? Does it look like April, whatever day is, 12th, 2020, whatever year it is, 2023? No. It just looks like something like planet Earth, but it doesn't reproduce what happened with Earth. So what we want to do is have this model, when it solves the equations, what comes out looks like what actually happened. That is the kind of big picture idea. So the way we do this is it's another technology. It's another technology, and we call it four-dimensional. It has a complicated name. Four-dimensional variational data assimilation, or four-dimensional variational assimilation reanalysis. It has all these different kinds of names. But the idea is that we want, we'll look at this idealized schematic, okay? In this cartoon, this figure on the top right, we have a couple different things. We imagine on the x-axis is time, and we have measurements. We have the measurements are the red x. And the red line is the simulation. The simulation, when the model solves the equations of motion. And we see between the observation at time 1 and time 2, the model goes to the red x, the black x. But the observation is at the red x, so they're different. The model goes this way, but the data says it's over here. So in traditional ocean reanalysis, what we do is we adjust the model. We say we have new data, the model is different than the data, we'll force the model to look like the data. This is the standard approach. Now that's okay, because in the end you can have a solution of the ocean that follows the data, but the problem is, if you look carefully, it jumps. It jumps. You have the model is looking good, then you have an observation, oh, bring it over there. And then it does this, oh, new observation, move it over there. So it jumps. And the problem with the jumping is that you can't keep track of where things went anymore. Here's an example. You want to know where the carbon dioxide is going. The model should simulate the carbon coming in, and it should simulate the carbon moving around. But if it doesn't have that right, and you just observe carbon somewhere, and you force the model to have carbon there, then where did it come from? You can't understand how it changed through time. So with ECCO, our goal is to make this blue line. It is a solution that fits the data as well as we can. It may not fit the data exactly, but it fits the data as well as we can, while also, and most importantly, maintaining the conservation laws. So we don't add energy, we don't add mass, we don't add salt, we don't add momentum, we stick to the physics. That's the physical oceanography part of it. We are very stubborn about the physics. We say it must be like the physics are right. And it's a little extreme. But that's the best that's the idea. So when we can make a simulation that fits the data as well as we can, and we make the blue line, we give that a name, we call that a state estimate. And with that, a student can investigate why something happens. They don't have to study all of every piece of data, because again, that's too much. They should understand the data. They should understand where it comes from. But when they have the state estimate, they can look at the state estimate. They can follow the physics. They can follow how the heat moved, how the fresh water moved. And they can do their thesis about that, as opposed to spending 3 years trying to collect all the different measurements. So that's the idea. Yeah. So here's just an example of two different approaches. Okay. Now this is just a simple example, and it shows the salinity of the North Pacific and the South Pacific. Okay. We just picked two volumes in the middle of the ocean. Okay. And the two curves are the blue curve and the red curve. The blue curve comes from ECCO. Okay? It obeys the laws of physics. And so from one moment to the next, because our physics are continuous, the solution evolves smooth. The red curve is from a different data product that's also extremely useful, but that data product only uses the Argo measurements. So every month, they take all of the Argo measurements everywhere that they came in the whole planet, and they make a map. They basically say, we'll just map it out. Standard, optimal interpolation, the same procedure that's been done since Bretherton 76. It's the same procedure, essentially. We map it out. So it looks, of course it follows the data. It is the data. But it's noisy. And you can't understand how things change because from one month to the next, there's no continuity. So this is just supposed to motivate you about why we want to make the blue curve as opposed to the red curve. Okay. And what's, I think, well, it's supposed to be an animation. I don't know how to make it go. But what's so nice about this is that we don't only, with these kinds of solutions, of course we can, I wish I knew how to make it play. Not only do we reproduce the altimetry and reproduce the sea surface temperature, but we also can see things that the model does things that we can't observe easily. For example, on the bottom right, that's the vertical velocity. The vertical velocities are like famously hard to measure globally because they can be very small and the measurements can be very noisy. But because we're solving all the equations, sometimes things have to come up and sometimes things have to come down. And the model equations, the physics, they tell us how that happens. So that's why I think it's useful. For real quantitative analysis, this is the kind of work that we often will do. We see on the left is like a time derivative of temperature at the surface, sea surface temperature. But we can look at the equation, look at the model, and ask what drove this? What are the drivers of it? Some of it is because of advection. That's the top right. Some of it is because of diffusion. That's the middle one. Some of it is because of atmospheric forcing. So we can disentangle the different terms that cause, at the left-hand side, the tendency. Okay. So that's enough of the motivation. I hope I can at least, you may not think, I'm not trying to convince you that this is the only way to do it, but this is what we do. And why I think it's a useful thing to do. So within our community, we've been, as I said, working on this for quite a long time. And what we have now is a solution that goes 30 years from 1992, with the first altimeters, until last year. So we have a 30-year solution. And over the last few years, our real motivation has been understanding sea level rise. So we made an extra effort because we know sea level rise is partly caused by warming ocean, we know it's also partly caused by the melting of the ice sheets. So with this latest version of our model, we had to include, we chose to include representation of Antarctica because we want the water to come from the right place. So that was the most recent theme. And you know, I keep talking about the physics. The model we use is the MIT GCM. Some of you maybe use ROMS if you use numerical modeling, but this is another ocean model. And we break the planet up into 1 degree cells. And this is just, in case you're a modeler, this might be of interest. And I'm happy to talk to any modelers later about the details of our simulation. So now I'm just going to show us some quick comparisons of the model of our state estimate with some observations. So, you know, fundamental ocean quantity is what they call the mean dynamic topography, the average shape of the sea surface. It dictates the shape and the scale of the Earth's ocean gyres. So on the top is from altimetry, and the bottom is from our solution, and it's good. The ocean, at least our simulation, matches the major gyres of the Earth. This one is maybe more relevant to us as a society. This is a map that shows the different rate of sea level rise. We all know that sea level rise is not uniform on planet Earth. In some places, it's rising much faster than others. In Ensenada, it's rising slower than the global average. Same with Los Angeles. In other places, like the Western Tropical Pacific, it's rising much faster. If you look at the Arctic Ocean, Western Arctic, it's rising very fast. So we want, of course, the satellites observe this, and we want to reproduce it with the physics. So that's a good test that it seems to work. This one I'm going to skip. All right. Lastly, this is important for sea level rise. It shows red and blue are places where the data is showing the ocean is warming or cooling. So on the left side, it's where the top left is where the ocean is warming red or cooling blue. On the bottom, it's where the ocean is getting saltier or fresher. And so the data, let's say the mapped Argo data is on the left, and the simulation of this is on the right. So that's another, test that the model is doing a good job at reproducing the data. Yeah. This one I'm going to skip. All right. So we have these. We have the simulation, and we can test it in these ways to make sure that it's working, that the technology is working. It's been 25 years we've been working on this. So yeah, if it didn't work, they would have stopped giving us money a long time ago. So yeah, it works. But what's different what's different through time is the model gets better, the data changes, the data gets better, and we extend the window in time. So let's say it still works, and we are happy that the data record keeps getting longer. We're very excited about, for example, the SWOT mission, because this is going to give us very soon an unprecedented view of the sea surface height at scales which have never been measured. That'll be a new technology challenge for us. How do we make use of this data? Can we separate the balanced motions from the unbalanced motions? Yeah. So for the community, we try really hard to make these fields available to everybody, for everyone to use. When I was a student, graduate student, I found a lot of ocean data very hard to use. So I personally want to make it easier for the next generations. I also feel that if it's sometimes when we work at a place like JPL or NASA or Scripps or Woods Hole, we forget because we work in it so intimately, we work with it every day, we forget how hard it is for someone from the outside to use it. So it's really my, like I said, my goal to make it easier to use. So what is it that we provide? We provide people the three-dimensional fields of how the ocean changes, the temperature, the salinity, the pressure, the density. We also provide the fluxes, the horizontal and vertical fluxes of heat and salt and momentum, so you can reconstruct, you can investigate for yourself why things changed. Part of the solution are the air-sea fluxes, which I know are important for a lot of investigations here at this institute. So we also provide our own estimate of wind stress and evaporation and so on. And a much more technical part of the solution are the three-dimensional coefficients of eddy diffusivity. That's a very technical thing in case you aren't a modeler, but that's important for people, other modelers, and for people who want to understand mixing in the ocean. Okay, so we provide that with the help of Professor Vasquez and other folks at JPL. All of the data for ECCO is available at this website called the NASA Physical Oceanography Data Archive Center. And all of the data is also now hosted in the cloud. So if anyone here is doing their analysis using cloud computational resources, the data is there. You certainly can also download it onto your own machines to do the calculations. NASA and other institutions are really pushing us to do all of the work in the cloud. Is it a good idea? Is it a bad idea? I don't know. No one knows how to work in the cloud. It sounds cool, but no one really knows what's going on, so we'll see. But that's where it is. We also recently developed some routines, a library in Python that are just specifically meant to help people analyze our output. This was the kind of thing where all of the students, we were all writing the same code. We were always writing the same analysis code, and we said, let's just put it together and make it an open source library and point people to it. Hopefully it saves you a couple of weeks, of work. Okay, lastly, on this topic, something that I think is very cool is we made a read the docs page of ECCO tutorials. And the idea is remove another barrier. Just make it even easier for people who know about physical oceanography to show them how to do certain calculations using our output. Because some of the calculations are like a little complicated. The heat and salt budgets are a little complicated, so let's make it easy for people with complete examples in Jupyter notebooks. Also, with another JPL colleague, we've started kind of lessons. So it's like almost like introduction to physical oceanography concepts using ECCO. So one of them, for example, is geostrophy. You know, it's the concept of geostrophy, and then we'll look in ECCO to see what geostrophy looks like in the ocean. Another one is Ekman transport, sphere drug balance. These kinds of fundamental physical oceanography ideas, we show how they look in this ocean model. So I think this could be, when I was a first-year graduate student, I wish I had that. Yeah. Okay, and now I want to tell you about this, our website. So our website, yeah, it's cool. It shows pictures and all this stuff. But one thing that I like about it that we've been really working on is to showcase applications. Again, the idea is help a student, postdoc, early career scientist understand what they can use the ECCO for. So every month or so, we go to the journal, we go to Frontiers, or we go to Journal of Physical Oceanography or Climate Dynamics, and we find a paper that uses ECCO. Because that's easy. There's like 150 publications a year that use ECCO, so every month I can pick one of 10. So we find one, and then we call up the author and say, do you want to make a story? And they mostly say yes. And we do what they call a story map. A story map. So first it introduces the fundamental concept, the science question, and then it goes through and shows how the scientists use ECCO for that application. And so if you write a paper with ECCO and you want to be highlighted, just tell us and we'll add it because we're always looking. But one example of a story map, which I think, Professor Gomez, this is the one that you had in mind. Yeah. I don't know how to click. Oh, no, it's the touchpad. This is one that was recent, and it has to do with upwelling. And this... Are you trying to I'm going to click on it, yeah.
I think it might be on the other, like if you push it far away from the...
Alina? No, it comes. It just may be slow, but it comes. Yeah. And I can slide down like this? Yeah. Yeah, so I just want to it's just cool. And there are a lot of these story maps. The person who makes them is really talented with outreach, and we're very lucky that she works with us. So I just want to kind of show you what one of these looks like. So this one has to do with upwelling. And upwelling is a fundamental ocean process that's super important for example, here, along the North American West Coast. Upwelling is important. It brings nutrients, and it allows all kinds of fisheries and economies related to fisheries to thrive. So what they do here, excuse me, yeah. So first they introduce the concept, why is moving water upward important? Then it shows, talks about phytoplankton, teaches people about what phytoplankton are. We have a beautiful map showing chlorophyll, and we'll all recognize along the eastern boundaries of the gyres that we have more chlorophyll than in the center of the gyres, because the upwelling is what's bringing the nutrients up. The phytoplankton need the nutrients, and when the nutrients are there, the phytoplankton make chlorophyll, and chlorophyll we can see from space. So these are all the places where the upwelling takes place. And now they talk about this study, which is a little different, which shows how there's also upwelling along western boundaries, although it's harder to see. And because it's harder to see, the study, it investigated the vertical velocities in ECCO along some western boundary regions. This one is the Kurishio off of the coast of Japan. And it shows, this is really an incredible, if I could do it, interactive map. And it shows this is a map of the vertical velocity of the ocean near the surface. Yeah, and then it's just incredible. They show how a similar upwelling happens on the U.S. East Coast. They show the structure, vertical structure of the upwelling and downwelling, and so on and so forth. So, there are many of these story maps. I learn, believe it or not, I learn about things about the ocean from looking at these story maps, even now. So I encourage you guys to take a look at that. Because it is, like I said, I think it's a cool thing that we've been doing. All right, if I can go back to this. I think here. Yeah, okay. And then, in the last few minutes of my talk, I wanted to talk about some future work that we're doing. One of them is high-resolution ocean model coupled to an atmosphere. So this is work that Dimitri Menemenlis, my colleague, and I are doing with folks at the NASA Goddard Center. I loosely mentioned before ocean biogeochemistry. This is a brand new area for us, but we think it's very important, and there have been some recent works adding ocean biogeochemistry into the ocean ECCO model physics. And if you're interested in ocean biogeochemistry, I think you should, you might find this also interesting. And lastly, we have, I just wanted to show this example of one of the highest resolution models that we have run. This is from our colleague Dimitri Menemenlis and Hong Zhang. And this is a global model at 1/48th degree. And I picked this because it has the Gulf of Mexico. And I understand that SESASI has a mandate to understand ocean circulation changes and ocean hydrographic changes in the Gulf of Mexico, fundamental ocean physics, not only on the west coast, but also on the Mexico east coast. So I think it could be interesting and useful for some of your research to have access to this kind of numerical model. No, at 1/48th of a degree, we can't afford it. We can't afford it. The supercomputers haven't gotten that big yet. But this kind of model is useful for process studies. How
long is the run?
16 months. Okay, and then very, very briefly, I want to highlight some cool work by this former student, Hector Torres. Hector, when he came to a former student, Professor Gomez, Hector came to JPL and he immediately started using our high-resolution simulations to continue his research into sub-mesoscale, mesoscale dynamics. And Hector is using these simulations to help conceive of a new mission, a mission that will measure ocean wind and currents, surface currents, using what they call Doppler scatterometry. So I don't have time to go into the details of the concept of Doppler scatterometry, but if you have, everyone is familiar with the Doppler effect, and the idea basically is that you shoot electromagnetic radiation down to the sea surface, and if the ocean is moving towards you or moving away from you, it will affect the return a little bit differently. And so if you could very carefully measure that shift of the return pulse, then you can make a map of ocean surface currents, in essence. So Hector is using the very high resolution ocean model as a test bed, where they simulate the spacecraft taking the measurement, and they ask the question, how well can I reproduce what really happened? So he pretends that the ocean simulation is reality. They put a simulated satellite over it, and they see what comes out. And what Hector has found is that the technology will probably work. And so he and a larger team of people are putting this proposal into NASA for a brand new type of satellite. So that would be very, very exciting for us. And this kind of just shows an example of what the ocean vorticity looks like at these different resolutions, because that's what he needs for this high resolution work. So what Hector is doing, I think, is a really cool example of application of ECCO for NASA. And if it wasn't for his training here at CSESI, we wouldn't have him. So we're very grateful, very grateful for that. And with that, I'm finished my talk. Thank you very much.
Questions? Yes, Professor Pavia.
Hi. First, let me thank you for a very interesting seminar. Oh, sorry. Well, thank you for a very interesting seminar. A few years ago, I was in China, and some biologists had billions and billions of samples, of biological samples. And I asked, phytoplankton, and I asked them, how many technicians do you have to analyze them, to analyze all the data, and how many microscopes? And they said, no microscopes, no technicians. Everything is analyzed with artificial intelligence. So when you said that there is no one who could understand all the data that you have, I don't know if you already thought about it. Maybe, most probably you have already thought about it, but maybe the way is just to use the artificial intelligence. If not, you're doing it right now. Thank you, and congratulations again. A very nice seminar.
Oh, thank you. I know I recently was talking to a scientist who told me about this application of artificial intelligence for phytoplankton. And as I understand the problem, I mean, the challenge they have is they collect billions of samples and they want to identify what the different species are. So the traditional way is they pass the sample through a screen with a microscope and a student counts. Traditionally. And now they train their artificial intelligence on 1,000, 10,000, 100,000 samples, and they ask it, please identify for me. And it's fast. The flow through the tube is very fast, and the artificial intelligence can take many pictures. And they've compared the output, what the artificial intelligence has reported versus the best human, and they look pretty good. So that would be helpful. So I think the application of artificial intelligence, we have to be clear about the question we wanted to ask. So if we want to ask the artificial intelligence why there is a harmful algal bloom off the coast of Baja, maybe it could answer that question. If it knew enough, if we trained it with enough physics and chemistry and biogeochemistry, maybe it could answer that. But we're very far from that kind of answer. But we can ask it other questions, like if we give it raw satellite data, the pulses, the energy return from the instrument, some very low-level basic measurement, we could train the artificial intelligence to tell us what the physical measurement is. For example, with salinity, what's measured is, energy flux at different wavelengths. What we want is salinity. So we can train, and people are trying to do this, to train the artificial intelligence to get us salinity from the low-level data streams. But for global physical oceanography reconstructions, we almost don't even know how to ask the question of how to train the AI. But people are thinking about it, and it's a very timely question that you ask.
Yes.
Hi, Ian. Thank you for your presentation. Looking at your maps from comparisons between ECCO and Argo, they look really similar. So this is kind of a rhetoric question. I was just wondering if you think we'll ever be able to blindly rely on instruments like ECCO and these models, so we can no longer correlate it with in-situ data. So we can just look at the model and forget about this on-site data. Do you think that will ever be possible?
No, and in fact, if I should clarify, the only reason the model that we make is as good as it is because we use the Argo data. You know, you can say it's kind of a machine learning, although we don't use that term really, or some kind of artificial intelligence, although we don't use that term. We have a system that helps us get the right simulation from the data. And it's a technical many hours of lecture to talk about that data assimilation method, but fundamentally we have as input all of the Argo data. And so the thing that we add is the physical connection between the data. But if we didn't have the data, we wouldn't have anything. So we really want the data to continue. In fact, the more the better. But the data can never tell us, the observations alone can never tell us about the time derivatives, because they're all snapshots. They're all just single snapshots, and they don't tell us about DDT. So we will always be advocating for the data.
Yes, Julia?
Are there any plans in the ECCO group to get involved in ocean forecasting? I mean, you do ocean estimation, but I wonder if there are any plans, particularly in the NASA group, whether you are still going to stick to this or are planning to do some forecasting?
That's a great question. Historically, the ECCO group has done no forecasting, as you maybe you know. In fact, I don't think we were even allowed to use the word forecasting. Yeah, we were not even allowed to use it. But there are the forecasting that we are doing these days is in support, two different types. One is in support of atmosphere forecasting. The idea is if we have a good reconstruction of the ocean until today, that would help a weather model forecast at seasonal timescales, because the ocean has a lot of memory, a lot of energy, and so on. So that's one direction that we are experimenting with. This is on 3 to 9, maybe 12-month timescales, but again, mostly to help the atmosphere people. The other forecasting that we've been doing is most recently related to sea level, and it's a little hard for me to explain it, but the idea is it's physics-based. We can ask the model, if you put wind here 6 months ago, how does sea level change in Ensenada today? So we can put that physical understanding together along with some other kind of forecast to make a prediction, but we're kind of limiting our prediction right now to very specific variables. Sea level, I think, is the one that is the easiest one for us to do. But in general, I would say no, the scope of ECCO right now is not to make 5-year, 10-year, 20-year forecasts of the global ocean.
Sí, gracias. Muy bonita, very nice talk. About the regional modeling, you showed some figures at the half-degree resolution, and you mentioned possibly finer resolution, GCM resolution. That's what you said. There will be finer than half-degree resolution modeling?
Yeah.
Excellent. But that's for the GCM?
The global, yeah.
Okay.
Yeah. There are right now we are working to do the global reconstruction 30 years, or even actually we've been asked to do 50 years. They want us to start in 1980. Even though there's less data, very less data, some communities have asked us for that. But anyway, the goal in the next 4 years is to do global 50-year simulation at 1/6 of a degree. Yeah, 1/6 of a degree. And we're at JPL right now, like on my Slack right now, that's the day-to-day technology development that we are talking about. How can we do a global reconstruction that long when the model has eddies? Because that's what makes it technically challenging. But that's our goal. 1/6 of a degree, 30-year, good reconstruction of the global ocean.
Excellent. Then I take the advantage to mention about a meeting that there will be in the ICTP in Trieste. We have the conference on CORDEX, is the Coordinated Regional Downscaling Experiment, that currently it includes only atmosphere. But now they want to include also the ocean, so there will be a special meeting to coordinate ocean modelers to have around the globe regional simulations for the ocean. So it would be nice. I can send the information to you and Hector.
Thank you.
And I have already shared with some people here.
Sounds very interesting. Thank you very much.
Tenemos preguntas de, last one. Paulina, please.
Thanks. I was just wondering, I'm curious about whether you're doing already data assimilation in the biochemistry models or not, and if so, which observations are there available? The BioArgos or?
Yeah.
That's it?
I think the BioArgos, I think, are one of the greatest sources. The type of data assimilation we're doing with the biogeochemistry data is it's early days. And partly because the observations are very different and less, right? The way that we constrain the model to those data is a little bit different. But I can show you 2 publications from the lead of that effort, and in those publications, they go into a lot more detail about all of the data constraints that they make. But it's very hard to see. But on the bottom left, this is the scatter plot. On the x-axis are observations of nitrate, chlorophyll, silicate, alkalinity, DIC, and dissolved oxygen. And on the y-axis is the reproduction from the simulation. And they're trying to say that at least at this early attempt, we can, on aggregate, reproduce the large-scale patterns. In the bottom right graph, it shows several different estimates of global carbon uptake. The black one is from our latest solution, and the Landschutzer one, which I believe is considered the state of the art in that community, is the light blue one. It's not a great figure, I'm sorry, from here. But the other kind of measure of success right now is that the model is simulating not just the pattern of CO2 uptake, but also the change of CO2 uptake over the last few decades. At least they agree with the few data and other estimates that they have. But I really think this is the next frontier. Yeah.
Tenemos preguntas en línea. Ok. Muy bien, miren, ahorita vamos a tomar el queso panilino y a la 1:30 está programada una reunión informal para intercambiar puntos ya un poquito más específicos del modelado. Les platico que ya tiene mucho interés en platicar del programa de desarrollo. Entonces, les damos las gracias allá. Thank you. Después del... Van a tomar un lunch.
Can I take a picture of you? Would you mind if I take a picture of you guys?
Sure.
For the NASA Twitter feed, yeah. I'll take two. I'll take two.